We're looking today at a hanging sign problem. The hanging sign problem is a plank that's attached to the wall and supported by a cable. Now that cable could be attached to an overhang or it could be attached to the wall itself. In this case, the sign is hung at the end of the sign pole, and the cable is attached to the wall. Using the scale, we find out that the pole itself is around 3.25 meters long based on what the scale tells us. And it's around 3.25 kilograms based also on the scale. The sign itself is 8 kilograms. Now, for a simplified drawing, we only want to look at the plank. We don't care about the wall, we don't care about the cable. Now, the forces acting on the plank is the plank itself acting at the center of mass, and also it's the sign hanging below the plank, and that's acting at the very end of the sign pole. Now, the tension is pulling at an angle from the end of the sign pole. That's pulling in and up, which causes the wall to have to pull in as well, and also has to push up to support that end of the sign pole. Now, we need to label these, so once it's labeled, we have a simplified drawing that's labeled. Now, notice that we don't have an angle for the forces acting at the wall. We don't know what that angle would be. We just know that there's a force that's up and a force that's inward that together give you the force of the wall. We also know that the tension can be broken down into a y component, which is t sine theta, based on where theta is located, and tx, which is the t cosine theta, which is again related to where the sine or the angle is located, theta. Now, we also label the distance from which the forces act. For example, L divided by 2 is the distance at which the weight of the plank acts, whereas the tension and the force of the sign act at a total length L. Now, next is the physics concepts. Now, the physics concepts at hand are static equilibrium. We would like to make sure that the object is meeting the two conditions required for static equilibrium. The first of which is the net force is equal to 0. The second is that the net torque is equal to 0. Now, in the equations, we're going to have three sets of equations. There's a sum of x and a sum of y. This is different from the past examples because there's usually only been two equations dealt with, and that was the force and the torque. But in this case, the force has been broken down into an x and y direction, as there are x and y forces. The x forces are fairly simple. The wall has to push in as much as the cable is pulling in order to give you a net force of 0 in the x direction. The y direction, the upward force of the wall and the upward force of the tension have to equal the weights pulling down. Now, as far as the torque is concerned, we first have to start by asking where's our pivot. And again, it's in static equilibrium, so it's not rotating. So we can pick our pivot. Now, we want to pick our pivot in a way that makes sense. So if we don't know the force of the wall and we don't care about the force of the wall, that makes a logical choice for the placement of the pivot. Now, once we've done that, we can then figure out the torques that are applied at that pivot point. Now, the force that's applied due to tension is t sine theta, as it's the perpendicular part of the tension times the length. And then the other forces, or I should say other torques, are going to be the weight of the sign itself and the weight of the plank. Now, those act in the distance from the plank being L over 2, because that's the center of mass, and the sign itself being the length of the pole. And again, no numbers at this point, because we really need to look at what's going on algebraically. Algebraically, we're going to start with the torque equation. Now, the reason why we're going to start with the torque equation is because the other equations have the force that's acting at the wall. So we don't want to focus on that because we don't know what those forces are. And we really only want to know, according to the problem, what the tension is. So once we solve for the tension, which requires getting all the algebraic information to one side except for the letter t, then we would actually be able to solve for what we need. Now, we can go ahead and get rid of the length in this equation because it's on all parts on the top and the bottom, and we wind up getting the fact that the length of the sign the sign pole really doesn't matter. And as far as the tension goes, we wind up with an expression for tension being G is the mass of the sign plus the mass of the plank divided by 2 divided by the sine of theta. Now, once we do this, we can then plug in numbers. Now, the numbers themselves would wind up giving us an expression, but we don't have theta. we'd actually need to be provided a theta in order to figure out this the actual tension. Now, once I just kind of assigned a theta of 35, I could then plug that in and figure out what the tension is supposed to be. And we wind up getting a tension of around 54.102, a bunch of numbers. We need to round that up to around 54 newtons. Now that's an example of a hanging sign problem. And that's it.